In this video, we're going to get started on sections 13.3 and 13.4 on the dot and cross products. So in this section, we're going to learn about these two operations with vectors. And these two operations we should think of like multiplication or taking products. But again, there's two of them, so it's important that we kind of keep track of which one's which. They both have very different meanings and outcomes, but very interesting and useful operations. All right, so let's get started first with the dot product. And we're going to begin with looking at an algebraic definition of the dot product. So this just means we're going to look at how to actually compute a dot product using two vectors. All right, so beginning here, let's let v and w be two vectors. So notice that these two vectors are living in 3 dimensions because we have an I, j, and k component. So k, I don't know if we've said this before, but is the component or the direction in the z-axis. Okay, so here are 2 vectors. Then the dot product, written v dot w, of v and w is defined as follows. So the dot product between v and w is, we're going to multiply the components on the I term, so v1, w1, multiply the components on the j term, multiply the components on the k term, and then add all of those together. All right, so notice that what we get in the end of a dot product is a number. So even though we started with 2 vectors, the output of the dot product is a number. We're just multiplying the components together, adding up, and we get a number. Okay, well, let's look at an example of actually computing a dot product together. So in example 1, we're asked to calculate v dot w if v is the vector I plus 2j plus 3k, and w is the vector 3i minus 2j plus k. So what we're going to do to find the dot product is to multiply the corresponding components. So we have 1 times 3, looking at the I terms, plus 2 times negative 2, looking at the j terms, plus 3 times 1, looking at the k terms. So we can add all those together. We get 3 minus 4 plus 3, which is equal to 2. So again, we see that the output here is a scalar, a number. All right, so let's look at example 2, where we're going to make sense of what this number is representing graphically. So in example 2, we're given 3 different vectors, or 3 different graphs of vectors. And we're going to in each case, we're looking at u and v. And what we want to do in each case is calculate the dot product of u dot v. So first, let's go and just calculate the dot product for each case. If you'd like to pause the video right now, I encourage you to do so, work out these dot products on your own, and then check back in on confirming your answers. All right, and when you've done that, or if you'd like to follow along, let's continue. So u dot v in the first case, well, we multiply our I component, so 1 times 3, plus j components, 2 times 1. So here we're going to get 3 plus 2, which is equal to 5. In this next situation, we multiply I components, so we get 3 times negative 1, plus the product of j components, 1 times 3. So we get negative 3 plus 3, which is 0. And in this last situation, we have 3 times negative 2, plus 1 times negative 2. So that gives us negative 6 minus 2, which is negative 8. All right, so there are the algebraic definitions or computations of the dot products. But let's take a look at how we can see these numbers graphically. All right, so in this first situation, and in actually all these images, let's go ahead and look at the angle between the vectors u and v. So we notice between u and v here, we have an angle theta. And we can see that this, well, actually, why don't we go ahead first and just compare all of the angles. So first we have this angle theta between u and v. Then we have an angle here that looks kind of like a right angle. And then here between U and V, we have an angle theta that would be an obtuse angle. So notice that our angles vary: acute, right, obtuse, and our numbers of the dot product vary. 5, a positive number, 0, 0, and -8, a negative number. So it turns out that the sign and value of a number corresponds to the angle between the two vectors, U and V. So in the first situation, we see that this angle, theta, is between 0 and 90 degrees, or 2 pi if we're looking at radians, or pi over 2 rather, if we're looking at radians. So here, theta is between 0 and pi over 2. And so that always happens, or when that happens, our dot product is going to be positive, bigger than 0. So there's no coincidence there. And it turns out when our angle is equal to pi over 2, or 90 degrees, then the dot product is going to be equal to 0. And if our angle is between 90 and 180 degrees, or pi over 2 and pi, then the dot product is going to be less than 0. So we have this super cool association and correspondence between the value of the dot product and something about the angle. And that something is telling us if our angle is acute, obtuse, or right, depending on the dot product, and vice versa. Very cool. All right, in the next video, we're going to continue working through this section and look at the cross product. Thanks for watching.